In this video, we're going to talk about partial fractions. Now, we're going to use partial fractions to help us integrate what are called rational functions. Now, a rational function is just a function that can be written in the form a polynomial divided by a polynomial. So really, our goal in this video is to be able to do these kinds of integrals, right? These are all integrals of rational functions, right? We have a polynomial divided by a polynomial. So how do you do these types of integrals? Okay, now sometimes like a u substitution will work, but in many of these cases, u substitutions won't work. And so we're going to do this method called partial fractions. Now, let me just say, partial fractions is really just a topic in algebra. Okay, it's really an algebraic technique that we're going to use to help us solve integrals. Okay, well, just for the fun of it, let's subtract these two fractions here, 1 over x minus 1 over x plus 1. Now remember, if you want to add or subtract fractions, you need to get a common denominator. So if you wanted to do 1/4 plus 1/6, you'd have to get a common denominator of, say, 12 or 24. Okay, now you can always get a common denominator by just multiplying the denominators together. So that's what we're going to do here. We're going to take 1 over x and multiply it by x plus 1 over x plus 1, right? That's really just 1. So this whole thing is the same thing as just 1 over x. And then minus, well, we're going to take 1 over x plus 1 and multiply it by x over x. Okay, and again, x over x is just 1. But notice now what we have, both denominators are x times x plus 1. Okay, so we have, first of all, x plus 1 over x times x plus 1, and then minus x over x times x plus 1. Okay, and now since we have a common denominator, we can actually subtract them. So now we subtract the numerators here, x plus 1 minus x. And of course, x plus 1 minus x is just 1. And so what we get is 1 over x times x plus 1, or in other words, 1 over x squared plus x. So this whole, this fraction here, 1 over x squared plus x, is equal to this difference of fractions here. Okay, now what good is this? Well, suppose we wanted to integrate 1 over x squared plus x. How could we do it? Okay, we could try like a u substitution or something, let u be x squared plus x or something. The problem is we wouldn't have the correct du. Well, it turns out if we knew that 1 over x squared plus x was equal to 1 over x minus 1 over x plus 1, which it is, then we could integrate each of those separately, and those integrals are not hard to do, right? The integral of 1 over x is just natural log of x, or natural log of the absolute value of x. The same thing with the integral of 1 over x plus 1. You can do a u substitution, letting u be x plus 1. It turns out you end up getting natural log of the absolute value of x plus 1. Now, here's the question, though. Here, I started out with 1 over x minus 1 over x plus 1, and I combined them together to get this one. But if I were to try to do this integral, I would have to know how to do this process sort of backwards. Okay, because I wouldn't have known ahead of time that this is equal to these two things. So taking this rational function and breaking it apart into these pieces here, that's called doing partial fractions, right? 1 over x minus 1 over x plus 1 is called the partial fraction decomposition of this. Okay, so the question is really, can we reverse this process that we just did? Okay, so is it possible to reverse this process? Yes, it's called doing a partial fraction decomposition. So how do we do this? Well, let's do an example. Find the partial fraction decomposition of 5x minus 10 over x squared minus 3x minus 4. Now, the first thing you want to do when you're doing partial fractions is to factor the denominator completely. And notice the denominator factors like this, x minus 4 times x plus 1. Okay, and then if you're in a situation where you have all linear factors, okay, so there's no like squareds or cubes or anything like that. If you have all linear factors and none of them are repeated, so I don't have like an x plus 1 and another x plus 1. Okay, I just have one factor of x plus 1, another factor of x minus 4. If that's the situation you're in, that's kind of the easiest situation, you can do your partial fraction decomposition as it'll be some constant over x minus 4 plus some constant over x plus 1. Now the question is, what are those constants? Okay, and we'll deal with situations later when we don't just have linear factors, and also if we have repeated factors. Okay, but how do we find the a and the b? Well, the idea is to take this equation, and by this equation I mean these things that I've written here, this equation, and multiply both sides of that equation by x minus 4 times x plus 1. Okay, notice if we do that to the left-hand side, the denominator cancels completely, and we're just left with 5x minus 10. Okay, if we multiply the right-hand side, this whole thing, by x minus 4 times x plus 1, I have to, first of all, multiply this term by that. And when I multiply a over x minus 4 by this, the x minus 4's go away, and I'm just left with a times x plus 1. Okay, now when I multiply b over x plus 1 times this, the x plus 1's divide out, right? They cancel, and we get b times x minus 4. So notice, when we take this original equation here and multiply it by this denominator, okay, that's what you always multiply, is this denominator here, we end up just getting the numerator on the left side, and on the right side we get this. Now, how do you find the a and the b? Well, there's a couple ways that you can find the a and the b. One pretty simple way is we want this equation to be true for all values of x. Okay, we want to find an a and a b where this equation is true for all values of x. In particular, it should be true for like x equals 4. Now, why am I choosing 4? Well, if I plug in 4 everywhere I see an x, notice this 4 minus 4 will be 0, and the b will go away. So if I let x be 4, on the left side, we're going to get 20 minus 10, which is 10. And if I let x be 4 on the right side, we're going to get a times 5, right, 4 plus 1, plus b times 0. So in other words, the right side will just be 5a. So 5a equals 10, so a is 2. Okay, and if we let x be negative 1, now why did I choose negative 1? Well, negative 1 is the value of x that will make this be 0. Okay, if we let x be negative 1, what happens to the left side? Well, we're going to get 5 times negative 1 is negative 5 minus 10, we get negative 15. On the right side, we're going to have a times 0, right, because negative 1 plus 1 is 0, plus b times negative 1 minus 4. So that'd be b times negative 5. So what we have is negative 5b equals negative 15, so b is 3. Okay, so actually, we found the partial fraction decomposition. We found that a is 2 and b is 3. So if you put 2 for a here and 3 for b here, if you were to add these two fractions up, okay, by coming up with a common denominator and simplify it, you would get this. Okay, so this over here is the partial fraction decomposition of this, or in other words, of this. Okay, so suppose we wanted to integrate 5x minus 10 over x squared minus 3x minus 4. How could we do this? Well, we could write this in terms of its partial fraction decomposition, right? This is equal to this. Okay, just algebraically, this is equal to this. We didn't do any calculus in that step. This is equal to this. Now, if we want to do these integrals, we can integrate them separately. Remember, the integral of the sum of two functions is equal to the sum of the integrals. So we can integrate this one. Now we can factor out the 2 here. It's a constant, bring it outside. And same thing here, we can bring the 3 outside. And now we can do a u substitution here where we let u be x minus 4. And we could do another u substitution here, only let me just call it w because I don't want to confuse it with this u over here. We'll call it w equals x plus 1. So dw is 1 dx. And so what we end up getting is 2 times the integral of 1 over u du plus 3 times the integral of 1 over w dw. And the integral of 1 over u du is natural log of the absolute value of u. We also get a natural log of the absolute value of w here. And finally, we can plug in what the u and the w are. And this is our final answer. Okay, so notice we've used partial fractions to help us integrate this rational function. Okay, now let's do another example. So let's use partial fractions to evaluate this integral. Okay, we have 11x plus 6 over 2x squared plus x minus 21. Now, if you try u substitution, it's not going to work so well. For example, if we let u be the denominator, the du would be 4x plus 1. But we don't have a 4x plus 1, we have an 11x plus 6. And it's not like 11x plus 6 is just some multiple of 4x plus 1. So let's use partial fractions to do this. Now, you can factor 2x squared plus x minus 21. It factors like this. Okay, 2x plus 7 times x minus 3. Now, notice, is that really true? Well, 2x times x is 2x squared. We have a 7 times x, that's 7x, and we have a minus 3 times 2x, that'd be minus 6x. So we have a 7x and a minus 6x, that becomes the 1x here. And finally, 7 times minus 3 is minus 21. Okay, so notice we have two linear factors here, okay, neither of which is repeated, so we can write this as a over 2x plus 7 plus b over x minus 3. Now here we'd multiply both sides by this denominator, okay, so multiply this by this, and then multiply this right side by this. And I've kind of skipped a step here, but notice the left side would end up being 11x plus 6. What would the right side be? Well, if you multiplied a over 2x plus 7 times this thing here, the 2x plus 7s would go away, and you'd just be left with a times x minus 3. And same thing over here. If we have b over x minus 3 times this, the x minus 3's will divide out. They'll cancel. And we'll end up with b times 2x plus 7. Okay, so now how do we find the a and the b? Well, there's a couple ways. Let me show you actually both ways. One way is to let x be 3 and then to let x be, well, what would it be here? What value of x would make this 0? Well, you could actually set this equal to 0 and solve it for x. You would get x equals negative 7 halves. Okay, if x is negative 7 halves, okay, so again, I didn't show that scratch work there, but 2x plus 7 equals 0. Solve it, you get x equals negative 7 halves. So let's plug those in. Well, if you plug in 3 for x, this left side becomes 33 plus 6 is 39. If you plug in 3 for x here and here, this becomes a times 0, so that just goes away. This becomes b times 13. Right, 6 plus 7. So we have 13b equals 39, so b is 3. Now, I've rigged this up to give us nice whole numbers for a and b, but sometimes if you were to just randomly write something down, you'd end up getting these crazy fractions. Okay, so you just have to mess with fractions. But I've rigged most of these up to give us nice whole numbers. Okay, now we do have a fraction here, x equals negative 7 halves. So if we plug in negative 7 halves everywhere you see an x, this should end up being b times 0, okay, which it is. If we plug in negative 7 halves here and negative 7 halves here, this is what we get. Now, 11 times negative 7 halves is negative 77 over 2, and we still have this plus 6, which is 12 over 2. Okay, we want to get a common denominator here. And then here we have negative 7 halves minus 3. That's negative 7 halves minus 6 halves. That's really negative 13 halves. So we have negative 13 halves times a is equal to negative 65 halves, right? Negative 77 plus 12 is 65. So it ends up being, if you multiply both sides by 2 to get rid of those 2's, you have negative 65 equals negative 13a, so a is 5. Right, so b is 3 and a is 5. Now, there's actually another way that we could find the a and the b, and you really do need to know both of these ways. Okay, so that was one way, picking values of x that will make this work. You really should know this other way, though. So how could we find the a and the b another way? So again, suppose we're in this situation here. We've multiplied both sides by this, and we end up with this equation. One way to do this is to let x be 3 and let x be negative 7 halves. The other way is to distribute the a here and distribute the b there. So we have 11x plus 6 equals ax minus 3a. So that's what I've written over here. And this would be 2bx plus 7b. Okay, now what we're going to do is line up the coefficients. So you're thinking of the a and b as being constants. And when I say coefficients, I mean we have a coefficient of x here, and then we have a constant. Now sometimes we'll have like an x squared, and we'll have a coefficient of an x squared. But basically what we're going to do is take the two terms over here that have x, right? ax and 2bx. And we're going to factor out that x, right? It is a plus 2b times x. Okay, and then we'll take the two terms that don't have x's, negative 3a and 7b, and put those over here. So notice the two terms that have the x here, when we factor them out here, this a plus 2b should end up equaling 11, right? The coefficient of x here should equal the coefficient of x there, and the constant here should equal the constant there. So notice you get a plus 2b equals 11, and negative 3a plus 7b equals 6. Okay, and that's really just a system of equations that you can solve for a and b. Okay, you can use like substitution or elimination or whatever. And it turns out if you do that, you'll end up getting a is 5 and b is 3, just like we had over here. Okay, in fact, you can check. If a is 5 and b is 3, this would be 5 plus 6 is 11. If a is 5 and b is 3, you'd have negative 15 plus 21 equals 6. Okay, now this method, you might think, why would I want to use this method? This method is harder. Well, it turns out there's a lot of situations where this method is much easier. Okay, and I'll do some examples like this. So you really should know both of these ways. Okay, well, now that we found the a and the b, right? Remember, it was 5 and 3 were the a and the b. How do we do this? Well, we do this just like we did before. Break this up into two separate integrals. You can pull the 5 out front, pull the 3 out front. Now, here, when we do this integral, you might think, well, the integral of 1 over x minus 3, that's just natural log of the absolute value of x minus 3. So 1 over 2x plus 7, that should just be natural log of 2x plus 7, or the absolute value of that. But it turns out, remember, if we do a u substitution, the du will have a 2 dx. So we need to put a 2 there and a 1/2 there. So really, the integral of 1 over 2x plus 7 ends up being 1/2 the natural log of the absolute value of 2x plus 7. Okay, so don't forget this 2 right here. So don't just think because, oh, I have the integral of 1 over something, it's just going to be natural log of that thing, right? That's only the case if when you let u be the denominator, the du, or the dw in this case, is 1. but it's not in this case, it's 2. Okay, so the point is, though, we can do this integral. Okay, and that's our final answer. Okay, now, so I mentioned here there are 2 different methods for finding the a and the b and the c and so forth. So we might have more than just a and b. There might be a, b, c, etc. So you can either plug in specific values for x, chosen wisely, right? We chose these values of x wisely. I chose 3 so that it would get rid of the a, and I chose -7/2 so it would get rid of the b. Okay, you can either do that, plug in specific values for x, or you can line up the coefficients here like we've done, lining up these coefficients and solve a system of equations, or you could use kind of a combination of those 2 methods. And often one method is much easier to use than the other. I think in this example, this method was easier over here, plugging in specific values. But there are other cases where this method is the one that you want to use. Okay, it's much easier. Okay, so just on your own, see if you can do this integral. Okay, so you might want to write this down, pause this video or something and see if you can come up with what this integral is using partial fractions. Now, so far we've dealt with the simplest case, okay, where the denominator can be factored into non-repeated linear factors, and where the degree of the numerator is strictly less than the degree of the denominator. So it turns out if the degree of the top is bigger than the degree on the bottom, you have a little bit of an issue. Okay, in fact, so we really have 3 issues here. What do we do if we have repeated factors? So instead of having like x plus 8 times x minus 3, what if we have x plus 8 times x plus 8? Right, that's a repeated factor. It happens twice. Or what happens if we have nonlinear irreducible quadratic factors? So for example, like x squared plus 9, you can't factor x squared plus 9. Okay, now x squared minus 9 can be factored. That's a difference of squares. It'd be x plus 3 times x minus 3. But x squared plus 9, you can't factor it any farther. So that's what's called an irreducible quadratic factor. Okay, what do you do in that situation? And finally, what about the other situation where the degree on the top is bigger than the degree on the bottom? Okay, that's another special case we have to deal with. So let's deal with these one at a time. So first of all, what do we do with repeated factors? Now, if we just kind of cavalierly went about this like we were doing before, there's going to be an issue. Okay, if we have x plus 3 over x plus 8 times x plus 8, you might think, oh, let's just do a over x plus 8 plus b over x plus 8, right? That seems reasonable. Okay, the problem is, and by the way, I put incorrect here because I don't want you to go back and look at these notes here and think, oh, this is the way to do it. This is incorrect. If you were to multiply both sides by x plus 8 times x plus 8, what would happen? Well, the left side would just be x plus 3, right? The x plus 8 and x plus 8 would cancel. The right side, you'd end up having, well, a over x plus 8 times this. Well, one of those x plus 8s would cancel with this, so you'd be left with a times x plus 8. And same thing with over here. We'd have b times x plus 8. Now, what if we let x be -8? Well, notice what would happen. We'd have -8 plus 3, okay, that's -5, equals a times 0 plus b times 0. Right, if we plugged in -8 for x. So we'd have -5 equals 0, and that doesn't even make sense, right? That's a contradiction. It turns out there's no value of a and b that will make this equal to this. Okay, and so what was the issue? The issue was that we had a repeated factor here. It wasn't like it was x plus 8 times x minus 5 or something. It's x plus 8 times itself. So what do we do when we have a repeated factor? So clearly we have a problem. We use the wrong form of the partial fraction decomposition. Now the correct way to do it is to do a over x plus 8 plus b over x plus 8 squared. Okay, now by the way, if this had been an x plus 8 cubed down here, in other words, x plus 8 times x plus 8 times x plus 8, the correct way to do it would be a over x plus 8 plus b over x plus 8 squared plus c over x plus 8 cubed. Okay, so you'd have an a, b, and a c. But it's not just x plus 8, x plus 8, x plus 8. It'd be x plus 8 squared, and then x plus 8 cubed. Okay, again, if that were a cube there. Okay, so let's check to see, does this really work? It turns out this is going to work. If we multiply both sides by x plus 8 times x plus 8, the left side will just end up being x plus 3, and I'm going to write it as 1x plus 3. You'll see why in a second here. The right side, we'd have a over x plus 8 times this. Well, one of these x plus 8s would cancel, and we'd be left with a times x plus 8. And if we do b over x plus 8 squared times this, well, both of those will cancel with both of these here, and we just left with b. Okay, now we could try plugging in a value for x like -8 or something, but let's actually do the other method. Let's line up the coefficients here. If we distribute the a, notice we get ax plus 8a plus b. Now line up the coefficients. Remember, just think of the a and the b as being constants here. So we're going to line up the coefficient of x here with the coefficient of x there. So a is going to be 1, right? Then we're going to line up the 3 with the constant term over here. Okay, so 3 will equal 8a plus b. Okay, well, how do we find b? Well, notice that a we already found was 1, so this is 8 times 1 plus b equals 3, or 8 plus b equals 3, so b is negative 5. Okay, and it turns out we now have the partial fraction decomposition for this, right? The a is 1 and the b is negative 5. And it turns out this is correct, right? If you were to add these two things together, get a common denominator, the common denominator would be x plus 8 times x plus 8, right? Or x plus 8 quantity squared. And this, if you were to combine those by getting a common denominator, it would end up equaling this. You can try it and see that it really works. Okay, so again, this lining up the coefficient method worked out pretty nicely. The system of equations is really easy. It was just 8a plus b equals 3 and a equals 1. Okay, but once you know the a, that really quickly gives us the b. Okay, now how do we deal with repeated factors kind of in general? So let's suppose we have this situation. We have some polynomial over a polynomial. Now I've given the bottom polynomial in factored form. Now this x plus 5 cubed, again, really means x plus 5 times x plus 5 times x plus 5. Okay, so what do we have? Well, we have one factor is just x. We can write this as a over x plus b over 9x minus 2 plus, okay, now here's our repeated factor. We're going to go c over x plus 5 plus d over x plus 5 squared plus e over x plus 5 cubed. Okay, and by the way, if it were to the fourth power, we'd do plus f over x plus 5 to the fourth power. Okay, and then we have another one here where we have a repeated factor, so we put f over 2x plus 7 plus g over 2x plus 7 squared. Okay, now what about this situation? Well, here the x is the repeated factor. It's repeated 3 times, so we write this as a over x plus b over x squared plus c over x cubed. Okay, and then we have plus d over x minus 7. And then this is a repeated factor, so we have e over x plus 8 plus f over x plus 8 squared. Now, I'm not actually going to find the a, b, c, d, e, f, and so forth here. That would take a long time. It would be messy, but I'm just trying to do these real big examples here so we at least get the correct form of the partial fraction decomposition. To actually find the a, b, c, d, and so forth, it would take a little bit of work here. Okay, now how do we deal with what are called irreducible quadratic factors? And I'll explain what that means in a second, but x squared plus 9 is an example of an irreducible quadratic factor. Now, what do we mean when we say x squared plus 9 is an irreducible quadratic factor? Well, what we mean is that it doesn't have any real zeros. There's no number that you can plug in here that will make this 0, so it can't be factored. Okay, when we say it's irreducible quadratic, we mean it can't be factored without using imaginary numbers. Okay, now x squared minus 9 can be factored, right? It can be factored as x plus 3 times x minus 3, but x squared plus 9 can't be factored without using imaginary numbers. Okay, and so, and there's no zeros of this. So there's no value of x that you can plug in here that would make that 0. Okay, so I'll talk a little more about irreducible quadratic factors, but basically it means you just can't break them down any further. Okay, so how would we do the partial fraction decomposition? So you might think, okay, let's do a over x plus b over x squared plus 9. Now, it turns out if we do this, though, this is not going to work. So I put a big thing here. This is incorrect. So what would happen if we try to do this, try to find the a and the b that would make this equal to this? Now, it turns out there's not going to be any a and b that's going to make this equal to this, and I'll show you why. So what would we do? Okay, we could attempt to multiply both sides by x times x squared plus 9. The left side would end up just being the numerator, would be what's left over, 7x squared plus 5x plus 18. On the right side, if we multiply this by this first term, a over x, the x and the x would cancel and we'd be left with a times x squared plus 9. Okay, and if we multiply this out here by x times x squared plus 9, the x squared plus 9 would cancel with this one, and we'd just be left with bx. Okay, and now, again, let's try to line up the coefficients. So what we have is this right side. We could distribute the a. We get ax squared plus 9a plus bx. Now let's write these in descending order. We like to write the x squared term, and then the x term, and then the constant term. So we have ax squared plus bx plus 9a. So we have to line up the coefficients. Well, if we line up the x squareds, notice that the a would be 7. Okay, if we line up the coefficients of the x, we would see that b is 5. And finally, we get 9a equals 18. So 9a equals 18 means a is 2. But that's a problem, right? A can't be both 7 and 2. right? It can be two different things. Notice lining up the coefficients, the x squared, we get the a is 7, but if we line up the 18 with the 9a, we get the a is 2. So that's a contradiction. It can't be both of those things. So what's the problem? Well, we used the wrong form of the partial fraction decomposition. So there's no a and b that's going to make this equal to this. So what's the correct way of doing it? Well, I'll show you in just a minute, but essentially the idea, let me just tell you here, is instead of putting b up here, you're going to put bx plus c in the numerator. Okay, so I'll show you that in just a second. But the x squared plus 9 is an irreducible quadratic factor, meaning that it doesn't have any real zeros, or in other words, it can't be factored into linear factors without using imaginary numbers. Now notice we could actually factor it, but we could factor it as x plus 3i times x minus 3i. If you try foiling that out, you would see that this really does work. But notice that we have imaginary numbers that we had to use here. But x squared minus 9 is not irreducible. So in other words, it is reducible because we can reduce it, right? We can factor it into x plus 3 times x minus 3. Okay, so what is an irreducible quadratic factor? It's a quadratic factor that has no real zeros. Okay, in other words, we can't factor or reduce it without using imaginary numbers. Now, how could you tell from the graph of a quadratic function whether it's reducible? Well, it turns out that if its graph crosses the x-axis, okay, or touches the x-axis, it will be reducible. And otherwise, it's irreducible. So irreducible just means that if you graph the parabola, right, its quadratic function is going to be a parabola. If it never crosses the x-axis, it's going to be irreducible. So notice the difference between x squared plus 9 and x squared minus 9. Which of these graphs cross the x-axis? Well, let's actually look here on Desmos. X squared plus 9 looks like this. Notice it never touches the x-axis. It doesn't have any zeros of this function, right? There's no value of x that you can plug in there to make it 0, so it never touches the x-axis or crosses the x-axis. On the other hand, if you did x squared minus 9, that's down here, notice it crosses the x-axis. In fact, where does it cross the x-axis? At negative 3 and 3, right? The zeros of the function, right? That's x squared minus 9. So notice x squared minus 9 can be factored. In fact, it can be factored as x plus 3 times x minus 3, right? Those are the zeros here. But x squared plus 9 is irreducible. Okay, it can't be factored. So any parabola, now the parabola could open up or it could open down, but if the parabola cuts through the x-axis, it's going to be reducible. You can factor it. If it doesn't cut through it, you can't factor it without using imaginary numbers. Okay, it has imaginary zeros rather than real zeros. Okay, now how about from the formula of a quadratic function, how can you tell whether it's reducible or not? Well, it turns out that if you're looking at a quadratic polynomial, right, a degree 2 polynomial, you could find the zeros using the quadratic formula. But notice you'll get imaginary numbers because you have a square root of b squared minus 4ac, the square root of this, what's called the discriminant. You'll get imaginary numbers if the discriminant is negative. Okay, but if the discriminant is positive, right, if it's greater than or equal to 0, so it's non-negative, it will be reducible. Okay, otherwise it's irreducible. So for example, x squared plus 9, by the way, x squared plus 9 is really like x squared plus 0x plus 9. So the a is 1, the b is 0, and the c is 9. If you're to work this out, the b squared minus 4ac would really be 0 minus 4 times 1 times 9. It'd be 0 minus 36, so it's negative 36 is negative. So in other words, you're getting negative zeros, or I'm sorry, you're getting imaginary zeros of your of this polynomial. Okay, but if if you did x squared minus 9, the b squared minus 4ac ends up being positive 36. Okay, so if you get a negative discriminant, it's irreducible. If you get a positive discriminant, it's reducible. Okay, so just try on your own. Okay, look at these two quadratic polynomials here, the quadratic functions. Which one is reducible? One of these is reducible and the other one's irreducible. Okay, so which one of these is the reducible and which is irreducible? So again, you could do this by graphing these, or you could do this by looking at b squared minus 4ac. Okay, now what's the whole point of all this reducible, irreducible stuff? Now, it turns out every polynomial that has real coefficients can be factored, and you can keep factoring it and factoring it and factoring it until what you end up with is just all either linear factors or irreducible quadratic factors. So if you ever have like a degree 3 factor, you can always break it down, or a degree 4 or degree 5, you can always break it down. Now, some quadratic factors, though, can't be broken down. So those are irreducible quadratic factors. Okay, so for example, if you have a 7th degree polynomial or a 13th degree polynomial, whatever you want, you can always keep breaking it down into factors until you end up with only linear factors or irreducible quadratic factors. Now, in actual practice, this might be really hard to do. Okay, it's hard to factor like a 7th degree polynomial, but it's always at least theoretically possible that you can break it down into either linear factors or irreducible quadratic factors. And this is a consequence of a famous theorem called the fundamental theorem of algebra. It's not the same as the fundamental theorem of calculus, the fundamental theorem of algebra. Okay, well, what was the point of all this, and how does this relate to partial fraction decompositions? Well, now, again, we said that if we have this right here, which we talked about before, we looked at this exact one. I tried to write it as a over x plus b over x squared plus 9, but it didn't work. Okay, because x squared plus 9 is irreducible quadratic. We can't break it apart any further. So how do we do this? Well, we can write this as bx plus c. Okay, so you do something x plus something over top of any irreducible quadratic factor. Okay, so if we do this, if we multiply both sides by the denominator now, this x times x squared plus 9, you always multiply by this denominator down here. You end up with the numerator being left on the left side, 7x squared plus 8x plus 18. On the right side, we have a over x times x squared plus 9. Well, the x will cancel the x, and you'll just be left with a times x squared plus 9. Here, if we do this times x squared plus 9s, the x squared plus 9s will cancel, and we'll be left with bx plus c times x. Okay, make sure you put that in parentheses. Okay, so let's line up the coefficients. So again, why do we want to line up the coefficients? Well, you could try to pick values for x to plug in. For example, let x be 0, and that term would go away. But there's no value of x you can plug in here that will make that 0. So we're kind of almost forced to line up the coefficients. Okay, but it's not too hard, though. If we distribute the a, we get ax squared plus 9a. If we distribute this x, we get bx squared plus cx. Now let's line up the coefficients. Notice we have an ax squared and a bx squared, so let's combine those together and factor out the x squared, and we get a plus b times x squared. This is really ax squared plus bx squared. And then let's bring in our x terms. We have a cx, and then let's bring in our constant term, okay, 9a. Remember, we're thinking of the a, b's, and c's as being constant. Okay, the x is like our variable here. And let's line up the coefficients. Well, the 7 should equal a plus b, okay, because those are coefficients of x squared. The c should be 8, so that's nice. We already have the c. And the 9a should be 18, so a is 2. Okay, so notice we have the a and the c. Well, what about the b? Well, a plus b, remember, was 7. But we already have that the a is 2, and so the b ends up being 5. Okay, so we get a is 2, b is 5, and c is 8. So our original thing ends up being 2 over x plus, what was it, 5x plus 8 over x squared plus 9. Okay, that's what I've written here. So we found our a, our b, and our c. And it turns out this really does equal this. Okay, if you were to combine these, okay, get a common denominator, add them up, you should end up getting this. Okay, so again, the key here was we had to use the correct form of our partial fraction decomposition. We couldn't just put b here, we had to put bx plus c over this irreducible quadratic factor. Okay, so let's find the form of the partial fraction decomposition. And I'm not asking you to actually find the a, b, c, and so forth. So the form of the partial fraction decomposition, by the way, is not related to the numerator over here. Now, the numerator, the one thing you have to check, though, you have to make sure that the degree of the numerator is less than the degree of the denominator. Okay, if the degree of the numerator is bigger than the degree of the denominator, we have another situation. But if the degree is less, then we can just break it apart like this. Now, again, the numerator doesn't affect the form of the partial fraction decomposition, but it will affect what the a, b, c, d, e, f, and g, and so forth are. Okay, so how do we do this? Well, we have a over x minus 3, that's just a linear factor, plus bx plus c over x squared plus 7. Right? That's an irreducible quadratic. Now, notice here we have an irreducible quadratic that's repeated. Okay, so how do we deal with that? Well, we're going to put dx plus e over x squared plus 25 plus fx plus g over x squared plus 25 squared. Okay, and then if this had been a cubed, we'd put, what would it be, hx plus I over x squared plus 25 cubed. Okay, now same thing over here. Now here's a question. This x squared, is that a repeated factor or is that an irreducible quadratic factor? Well, it's a repeated factor. It's not irreducible because it's x times x, right? You can break it apart, right? So it's a repeated factor of x. So it's a over x plus b over x squared. Okay, if this had been an x cubed, we'd have to put plus c over x cubed. Okay, then we have plus c over x plus 2. Plus, well, we have a repeated factor, d over x minus 7, plus e over x minus 7 squared, plus f over x minus 7 cubed. And finally, we have an irreducible quadratic, so we put gx plus h over x squared plus 4. Okay, so that's the partial fraction decomposition, or at least the form of the partial fraction decomposition, okay, the PFD, partial fraction decomposition, of this rational function. Okay, so let's do an example where we actually do an integral, okay, that involves one of these irreducible quadratics. So we want to integrate this this rational function. Now notice the degree in the numerator is 2. If you were to FOIL out the denominator, it'd be degree 3. So we're okay. The degree of the top is less than the degree of the bottom. Again, I'll explain what happens if that's not the case later. But let's do some scratch work. So we want to find the partial fraction decomposition of this. Now again, I already gave it to you in factored form here. So what do we have to do? Well, it's a over x plus 4 plus bx plus c over x squared plus 9. Now we got to find the a, b, and the c. So we're going to multiply both sides by x plus 4 times x squared plus 9. The left side just ends up being the numerator. The right side, we end up with a times x squared plus 9 plus bx plus c times x plus 4. Okay, now we could try to line up the coefficients, but maybe a quick thing that we could do that would make things a little easier, instead of having to solve a messy system of equations, we could let x be negative 4 here. If we let x be negative 4, notice this will be 0. Okay, this whole thing says negative 4 plus 4 is 0. So we'll end up with just an a. The b and the c will go away. So if we let x be negative 4, this whole left side ends up being 192 minus 116 plus 49. So if you plug in negative 4 for x here and here, which ends up being 125. And if you plug in negative 4 over here, you're going to get 16 plus 9, which is 25. So we have 25a. And this all is 0 because of that. So we end up having 25a equals 125, so a is 5. Now again, I've rigged it up to give us a nice whole number like 5. If you try some problems in the book or you just randomly make your own problems, you might end up with things like 7/13 is what a is or something. But I've rigged it up to give us a nice number. Okay, well now that we know what a is, let's actually just plug in a equals 5 right here. Okay, we plug in 5 for a. And now we're going to do the line up the coefficient method. So we've kind of combined our two methods. We put in negative 4 for x here. Now there was no number we could put in for x here that would make that 0. So we're kind of, once we plugged in the negative 4, we can't really plug in any other numbers that are going to make it nice. Anyway, so let's do the line up the coefficient method. So now that we know that a is 5, plug in 5 here. So we get, and distribute the 5, we get 5x squared plus 45. If we FOIL this out, so we get bx times x is bx squared. You're going to have a cx from multiplying the inside terms and a 4bx from multiplying the outside. And finally, by multiplying the last terms, you get 4c. Now, combining our like terms here, right? We have a 5x squared and a bx squared. That becomes 5 plus b times x squared. Right? If you distribute the x squared, you'll see you get this term and this term. Now, we also have a cx and a 4bx. So that ends up being 4b plus c times x, right? Again, if you distribute the x there, you see you get this plus this, right? Both terms have an x there, so what we did was factor it out. And what are the terms that don't have any x's? We have the 45 and the 4c, so the 45 plus 4c. Now let's line up the coefficients. Well, 12 is equal to 5 plus b, so b is 7. Okay, now it's good that we knew that the b that was 5, otherwise we'd have a plus b is 12, and so that wouldn't give us what the b is quite yet. Okay, then let's set up 45 plus 4c equals 49. And if we do that, we get that 4c will be 4, so c is 1. Now, just as kind of a check to make sure we did this correctly, we already have our a, b, and c. Right, our a is 5, our b is 7, and our c is 1. If we plugged in those values for b and c here, would that line up with the 29? It should if we've done everything correctly. But notice if we plug in 7 for b, that'd be 4 times 7 is 28. And 1 for c, 28 plus 1 is 29. It does line up. Okay? And so we really do have everything done correctly here. Okay, now how do we actually do this integral? Notice these problems are a little long, right? You had to find the partial fraction decomposition, and then we have to do integrals. So we've written the partial fraction decomposition here, right? Our a was 5, our b was 7, and our c was 1. Okay, so we have this. We can split it up into two integrals. The first integral, you can bring out the 5. You can do a u substitution where u is x plus 4. It ends up being this as your final answer. Now, how do you integrate this? Okay, now look at this carefully. How would we integrate this? We could try a u substitution here. The u would be 2x. The problem is we have 7x plus 1. If we didn't have the plus 1, then that method would work fine. So how do we do this? Well, it turns out we can just use algebra here and rewrite this as 7x over x squared plus 9 plus 1 over x squared plus 9. Okay, this is really just algebra. 7x over x squared plus 9 plus 1 over x squared plus 9. And then we'll split that up into two different integrals, right? Integral of the sum is the sum of the integrals. This integral over here is going to involve an arctangent, right? An inverse tangent. In fact, if it had been 1 over x squared plus 1, it would just be arctangent of x. Okay, but we have a 9 there, so we have to do something. Here, we do a u substitution. We let u equal x squared plus 9. du is 2x dx. Now, we bring this 7 out front. We don't have the 2, so we write in the 2, and then we have to put a 1/2 out here. So notice we get a 7/2 times the integral of 1 over, well, I called it w actually because I didn't want to confuse it with this u here. We have 1 over w dw. Okay, again, the 2x dx was the dw right here. Okay, but don't forget that 2 there. Okay, so we end up getting 7/2 natural log of the absolute value of w, but w was x squared plus 9. Okay, now how about the 1 over x squared plus 9? Well, there is a formula that you could use, but the only one I remember for tangent inverse is that 1 over x squared plus 1. The integral of that is tangent inverse. So what could you do to get a 1 there? Well, you could factor out a 9. Right, this is 9 times 1/9 x squared plus 1. And then write 1/9 x squared is 1/3 x quantity squared. Okay, and then do a u substitution. Now, I already used u and w, so let me just call this v here. So if we let v be 1/3 x, the dv is 1/3 dx. So I need to put in a 1/3 there, and if I put in a 1/3 there, I'll need to put a 1 over 1/3 out here, or in other words, a 3 out here. Okay, and then 3 times 1/9 is 1/3. This 1/3 dx becomes the dv, and we have 1 over v squared plus 1. And the integral of 1 over v squared plus 1, dv, is just tangent inverse of v, and finally plug in what the v is. Now, alternatively, instead of going through all that work, there is actually a formula for 1 over x squared plus a squared. Okay, now I just remember it when a is 1 that the answer is just tangent inverse, right? If a is 1, notice the right side is just tangent inverse. But it turns out if a is like 3, so if you have 1 over x squared plus 9, which is exactly what we have here, the a is 3, we get 1/3 tangent inverse of x over 3, or 1/3 x. And notice that's exactly what we have here. So if you did have this one memorized, then you could kind of skip from here all the way on down to here. Okay, but I usually don't remember. I have a hard time remembering, okay, where was the a? Was it on the top or the bottom? How did this work out? And then the a, remember, is not the 9. The a is 3, right? Okay, but the point is, we were able to come up with our answer. Now, we had to use a tangent inverse here. So remember, sometimes when we do these irreducible quadratics, you have to break this apart into 7x over x squared plus 9 plus 1 over x squared plus 9. One of them, you end up doing a u substitution. You end up getting a natural log. The other one, you end up having like a tangent inverse. Okay, so it's good that we knew the integral of 1 over x squared plus 9, knew how to do that, right? It involved tangent inverse. Okay, so on your own, why don't you try one like this? So maybe you can pause this video and just see, can I figure out how to do this? So what would be the form of the partial fraction decomposition? Notice it would be a over x plus bx plus c over x squared plus 1. This one actually works out a little nicer because we have x there instead of, what was our other one up there? It was like x plus something, x plus 4. And also the other over here, it's nicer because instead of x squared plus 9, we just have x squared plus 1. So try this one and see if you can come up with the answer. Come up with a partial fraction decomposition and then actually do the integral. Okay, now let's do an example here. I don't think we've done an example where we actually did the integral where we had a repeated factor. Okay, so we want to integrate this thing right here. And again, notice the degree of the numerator is 2, the degree of the denominator is 3. So that's good. The degree in the denominator is bigger. Again, at the very end here, in the last minute or two, I'll end up showing you how you deal with the other situation where the degree on the top is bigger than the degree on the bottom. What you end up doing is long division, right? Polynomial division. Okay, but we can do the partial fraction decomposition here. Okay, and so how do we do that? Well, remember, it's a over x plus 1 plus b over x plus 5 plus c over x plus 5 squared. Okay, so we're going to multiply both sides by this. Okay, and we end up with the left side here, the numerator on the left side being over here. We end up with a times x plus 5 squared, because the x minus 1's cancel. And then b over x plus 5 times this, we're going to have one of these x plus 5's cancel with that, but we still are left with an x minus 1 times x plus 5. And finally, if we multiply this term by this, the x plus 5 squareds will cancel, and we're just left with c times x minus 1. Okay, now if we let x be 1 and x be negative 5, that's going to help us find the a, b, and the c. So if x is 1, notice what happens. This will be c times 0. This will be b times 0. Okay, times 6. But b times 0, that's going to be 0. And if we let x be 1 here, we'd have a times 36. We have 36a equals, well, if you plug in 1 for x, you get 4 plus 47 plus 93. It ends up giving you 36a equals 144. So that gives us the a is 4. Okay, now if we let x be negative 5, notice what's going to happen is we'll get a times 0, and this will still be b times 0, because plug in negative 5 here and here, this one becomes 0. But we'll have c times negative 6, right? Negative 5 minus 1. So we have negative 6c equals, well, if we put negative 5 in on the left side, it turns out we get this, and we end up getting negative 6c equals negative 42, so c is 7. Okay, now how do we find the b? Okay, the problem is if we're plugging in a negative 5 or a 1, these things get 0, and so we can't find the b by just plugging in numbers. So how do we find the b? Well, what we can do is let the a be 4 and the c be 7 and just multiply everything out here and then line up the coefficients. Okay, and I've done that over here. It's a little messy here, but you do 4 times x plus 5 squared because a was 4. Now, x plus 5 quantity squared is, remember, is not just x squared plus 25. It's x squared plus 10x plus 25. So you have to do x plus 5 times x plus 5. If you FOIL out x minus 1 times x plus 5, you get this. Okay, then we're going to distribute the b, distribute the 4. We also distribute the 7 over here. And we get this. We combine our x squared terms. So we have a 4x squared and a bx squared. So that's 4 plus bx squared. We can combine our x's. We can combine our constants. This is what we get. And then we line things up. So we end up with 4 plus b equals 4. So b is 0. And you can check, by the way, all these. If b is 0, this will equal 47. And if b is 0, this will equal, oh, I put 9, but that's supposed to be 93 there. Yeah, it's supposed to be 93. I accidentally did that. But if b is 0, this would be 93. Okay, so notice what we have here is we had our a was 4, our b was 0, and our c was 7. That's what we came up with. Okay, so how do we integrate these? Well, let's do the integral of the sum is the sum of the integrals. Now the integral of this one, of course, is just going to be 0 because that's 0. Okay, but we can take out the 4 from the first integral, take out the 7 from the second integral. This first one we do with a u substitution, letting u be x minus 1. We get an integral of 1 over u du. Well, if we let w be x plus 5 here, and dw is just 1 dx, we end up with 1 over w squared. Now that's not going to involve a natural log. Right? If it were 1 over w dw, it'd be natural log of w, or natural log of the absolute value of w. But 1 over w squared, that's something that we knew back in calculus 1, right? We can rewrite this as w to the negative 2, and the integral of w to the negative 2 is w to the negative 1 over negative 1, which ends up being negative 7 over w, this whole thing. So this w to the negative 1 can become a w to the positive 1 down in the denominator, and this negative can actually come out front. Okay, and then you plug back in what w is, just like over here you plugged in what the u is. So this is your final answer. So notice this integral here, we had the squared, did not involve a logarithm. Okay, so there was an example where we did one with a repeated factor. Okay, so on your own, why don't you try one like this? Now, how would you do this? Notice you need to factor things first of all. Notice both terms have an x squared in here, so you could factor this as x squared times x minus 7. Okay, now that has a repeated factor because the x squared is your repeated factor, so you'd end up having a over x plus b over x squared plus c over x minus 7. Okay, so again, you factor out the x squared here. So try that. Okay, now the very last thing, by the way, actually not quite the very last thing. It's a long video, I know so far. But suppose that we had done a partial fraction decomposition and we had gotten the following. Okay, how would we actually do this integral? Okay, well, this first one is going to involve a natural log, and so is the second one. Okay, so if we work things out here, this one, in fact, let me these were the integrals that we had. How do we integrate this last one? Again, we write it as 6x over x squared plus 1 plus 5 over x squared plus 1. We can pull the 6 out front and the 5 out front. This one is going to involve a tangent inverse. In fact, it just is tangent inverse of x. We have a 5. This one is going to involve a u substitution where u is x squared plus 1. We end up getting this. Okay, this one's going to involve a w substitution where we have like a 1 over w squared, so we don't have a natural log here. But these ones do involve natural logs, and this one has a 7/2 natural log of 2x plus 5, the absolute value of 2x plus 5, because when we did our u substitution, we ended up with a 2 there. So that's why we have this 2 down there. Okay, so just make sure that once you've done the partial fraction decomposition and you get something like this, that you know how to integrate this, right? You break it apart. Okay, and the very last thing is, what if the degree of the numerator is greater than the degree of the denominator? So we have something like this, x squared minus 8 over x plus 3. Okay, how do we do an integral of this, right? Where the degree of the numerator is bigger than the degree of the denominator. Okay, bigger than or equal to. Okay, well, we then need to use long division of polynomials. So let me just explain this here in the last 2 or 3 minutes here. What is long division? Well, remember way back in elementary school when you're trying to do something like 426 divided by 5, which, by the way, you could write it a couple ways. 426 divided by 5 or 426 over 5. Right? They mean the same thing. Okay, so we want to divide 426 by 5. What you do is you put 426 here and you put this little division symbol. Now, it's not a square root symbol, by the way. It's a division symbol. You put the 5 up front and you ask, how many times does 5 go into 4? Well, 5 doesn't go into 4. So you look at 42. How many times does 5 go into 42? Well, it goes in 8 times. And 8 times 5 is 40. Remember, what you do is you subtract, right? You have 2 left over here. 42 minus 40 is 2. You bring down the 6. Then you say, how many times does 5 go into 26? Well, it's 5 times, right? 5 times 5 is 25. So you do 26 minus 25 of 1. Now, back in elementary school, I don't even really like this, but they have you put R1, right? Remainder 1. 85, remainder 1. But what that really means is 85 and 1/5, right? 85 plus 1/5, or 85 and 1/5, or 85.2. Okay, well, it turns out we can do the same thing with polynomials. Suppose we want to divide one polynomial by another polynomial. So again, we're doing something like this over this, right? Notice this is a rational function. We're doing this polynomial divided by this polynomial. How do we do this? Well, we take this polynomial and put it under here. Now, I have x to the 4th. Now, notice there's no cube term, so I write 0x cubed. Okay, plus 3x squared, and notice there's no x term, so I put 0x. And then minus 8. And out front, we have x squared minus 2x plus 1. By the way, if you were missing like the x term, you'd have to put a 0x out front as well. Okay, well, how do we do this? Well, what we say is we look at the x squared here and the x to the 4th. Okay, the first thing out here and the first thing there. We say, how many times does x squared go into x to the 4th? Or in other words, what times x squared would give you x to the 4th? Well, x squared times x squared would give you x to the 4th. So we're going to put x squared here. And by the way, we put it way over here because we're going to line up all of our columns here. So x squared times this whole thing now, we get x squared times x squared is x to the 4th. X squared times minus 2x is minus 2x cubed. And x squared times 1 is x squared. Now what we do is subtract. So I would make sure you put this whole thing in parentheses though, because you're subtracting. You're not adding. So you don't do 3x squared plus x, it's 3x squared minus x squared, that's 2x squared. So start at the beginning. By the way, these things should always disappear. You have x to the 4th minus x to the 4th, that goes away. But you have 0x cubed minus a negative 2x cubed, that's positive 2x cubed. You have 3x squared minus a 1x squared, that's 2x squared. Then you bring down the next thing, which is 0x. Now you ask, how many times does x squared go into 2x cubed? In other words, what times x squared gives you 2x cubed? Well, x squared times 2x will give you 2x cubed. Okay, so you put the 2x there. And now you do 2x times this whole thing. So 2x times x squared is 2x cubed. So again, these things should line up. They should match up. 2x times minus 2x is minus 4x squared. And 2x times 1 is 2x. And now we subtract. And again, put it in parentheses here. Because otherwise you'll get goofed up, and it's very easy to make a mistake here. So 2x cubed minus 2x cubed, that goes away. Now we have 2x squared and we have a minus 4x squared. You might be tempted to put minus 2x squared, but remember it's a minus, right? It's plus. So 2x squared plus 4x squared is 6x squared. And again, you might be tempted to put a plus 2x here, but it's 0x squared minus a positive 2x. So it's negative 2x. Finally, bring down the negative 8, and you ask how many times does x squared go into 6x squared? Well, x squared times 6 will give you 6x squared. So we put 6 there. 6 times this whole thing is going to give us 6x squared minus 12x plus 6. If we subtract these, 6x squared minus itself is 0. Negative 2x squared really plus a 12x. Minus a negative 12x plus 12x. Negative 2x plus 12 is positive 10x. And negative 8 minus 6 is negative 14. So we're left with a remainder of 10x minus 14. But what that really means, remember, is plus 10x minus 14 over this thing here. So actually, this rational function is actually equal to this. Okay, so that's called long division. Now, by the way, if you just have a linear factor here, there's something called synthetic division that you can do, but it doesn't work if you're dividing by like a quadratic or a cubic or something. But you can use synthetic division if you want to in those situations where you have a linear, just like x plus something, or like x plus 7 or x minus 3 is the thing that you're dividing by. So by the way, if you wanted to do the integral of this, how would you do it? Well, you'd do the long division. Notice the degree of the numerator is bigger than or equal to the degree of the denominator. So we do this long division, we end up with this. Now, how do we integrate these? Well, it's easy to integrate x squared. It's going to be x cubed over 3. It's easy to integrate 2x, right? It's going to be x squared. Easy to integrate 6, it'll be 6x. How do we integrate this? Well, we have to use partial fractions now, right? So this is a long process here. Now, it turns out this one is actually just a repeated factor. It's actually x minus 1 times x minus 1 gives you this. And so it turns out if you do the partial fraction decomposition, I did this some scratch work. It's not easy to get from here to here, but if you do the partial fractions, it turns out you get 10 and minus 4. Okay, not minus 14. Turns out you get minus 4. But this is what your answer is, and then you can integrate these. This one will involve a natural log. This one won't. But the point is, that's how you deal with when the degree of the numerator is bigger than the degree of the denominator. So you might want to go back and remind yourself how to do this polynomial division. Okay, well, this is a long video, but there's quite a bit to explain. But we've explained how we can use partial fractions, this algebraic technique, okay, of partial fractions to actually evaluate integrals of rational functions.